Good morning to everybody, and thank you, the organizers, for this opportunity to talk here. And so now we are switching back to nuclear physics, and I want to talk about my project. So as you can see, I'm trying to mix constraint and DFT, density functional description, using ab initio simulations of nuclear matter. So just a brief introduction. Well, you probably know that the nucleus is, for the theoretical point of view, a complex interacting quantum body system. And perhaps for those who work in cold atoms in particular, it is useful to have a glimpse at the so-called nuclear chart. And here you can see what nuclei exist basically as a function of the neutron number and the proton number. And you can see the stable nuclei are only a small fraction of the nuclei which are known to exist, which are about 3,000. And there exists also a very large unexplored territory. I mean, unexplored because there are few or no experiments about this, but some theoretical estimates tell that there may be some other 3,000 or 4,000 nuclei still to be discovered. And some open questions in the field are actually related to this unexplored territory, or in general to the limits of the stability. So, for example, what are the limits itself of the nuclear chart? Those are that are called drip lines. Well, also it is often quoted that can we understand nucleosynthesis processes. And from the theoretical point of view, there's also the very broad question that is, can we devise a unified theoretical model? Because I mean, in nuclear physics, there are many different approaches, and they have different, to some extent, different domains of applicability. And in particular, in this talk, I will describe the density functional theory from one side and the broad class of ab initio methods on the other one. So a brief definition of ab initio could be the following. There is ab initio methods aim at solving the Schrödinger equation using two elements. First, a realistic model of the nuclear interaction, and second, a called suitable many-body technique. I mean, a many-body technique which is deemed to be exact or at least systematically improvable. Examples of ab initio techniques are quantum Monte Carlo, couple cluster, Green's functions, and so on. So the interest in ab initio lies that it is a fundamental and potentially accurate approach. And here for nuclear structure, I mean both infinite nuclear matter, and finite nuclei, of course. However, as you can imagine, ab initio is very computationally demanding. So I show you a picture taken from a very interesting review on the topic from 2 years ago. And you can see that ab initio, to a large extent, is limited to the corner of the nuclear chart. Actually, there are many progresses. Sometimes you can reach medium or even a heavy mass nuclei, but still it's very, very computational demanding and complicated. Well, as we'll briefly describe, density functional theory, the DFT here, can basically be applied to the whole nuclear chart with, I mean, it has a very, very large domain of application. So I don't know if you're familiar with DFT anyway, here different perspectives taken, and the key object is what is called the energy density functional, E of rho, which is basically a functional map between the total energy of a generic system and the densities which characterize the system itself. So here I list them. I remember that DFT was introduced in condensed matter and for the electron gas, basically, where a theorem states that there must exist this map between the energy and the densities. Then it was adapted to nuclear physics, and here I show you the general structure of the EDF, of the nuclear EDF. Actually, I'm just considering time-even systems, but that is enough to have an idea of what this model works. In practice, we have that the energy is the integral of, well, kinetic term plus density dependent term. This rho tau leads to an effective mass. Then there are density gradient terms and the spin orbit contribution. That more or less is the basic structure we are going to discuss. Then the idea is that basically once we have an answer for the EDF, the variational principle can be used to build a set of self-consistent single particle equations. So basically the idea is that an interacting system is mapped to a sort of fictitious, effective, non-interacting problem where there are only single particle states which move in a self-consistent potential. So this is a single particle Schrödinger equation, basically, but it must be solved iteratively. That's the basic idea. And okay, I already told that the whole nuclear chart can be studied with DFT, and now I'll briefly describe the ground state problem. But actually, a DFT framework is also the basis of, for example, studies of collective excitation, RPA, and so on, or can be applied to neutron stars and so on. So I will focus mostly on the ground state here, but actually, there's much more that can be done. And also, it's important that a good overall accuracy can be achieved. And for example, nuclear masses can be reproduced with an accuracy with respect to experiment of 1 or 2 MeV, more or less, and radii with an accuracy of 0.1 or 0.2 Fermi, just to give rough an idea, which is, I mean, it's quite good. So I just mentioned that DFT is in principle an exact theory because there are theorems that state that the energy function exists, is unique, and so on. But in practice, the EDF is known only approximately, because knowing the EDF, it would be the same as knowing how to solve the many-body problem exactly. And what is important to know is that currently most nuclear EDFs have an empirical character. With this, I mean that a functional form is chosen using symmetry arguments, heuristic arguments, and a lot of experience from past decades, basically. And then once the model is set up, a set of parameters, which are maybe around 10 or 15, something like that, is fitted on experimental data. Typically, these data are binding energies and radii from stable nuclei. And that implies a sort of bias in the EDF models, because you see here near the stability valley, where the EDFs are typically fitted, you get a good agreement between the different EDF models. There are plenty of EDF models actually, and they tend to agree quite reasonably well with experiment. So here, everything's not everything, but I mean, the DFT works pretty fine also with the current EDFs. But I just show you a paradigmatic example from a Nature paper, quite famous Nature paper, which shows that, for example, if you try to predict the neutron drip lines, that is the boundary between stable and unstable system, basically in this neutron-rich region, you see that there is no clear consensus because different models tend to disagree and disagree more and more as you go away from the stability valley. So, I mean, I was just saying this is just a paradigmatic example, but I mean, I used that to introduce the question that is, how can we improve the EDF accuracy also in regions where there are few or no experimental data? How can we somewhat reduce the bias towards the stability valley? So, from one side, we have ab initio, so it's fundamental and at least potentially unbiased. DFT, on the other hand, is universally applicable. So the question is now, can we use ab initio to constrain nuclear DFT? So I must say that there are, I just mentioned a few of several attempts at non-empirical EDFs, which follow. These are recent papers which show that, I mean, there are several ideas in this about trying to really exploit ab initio to give this higher level effective description. Also mentioned that Daniela Quaglia, we talked this, and also Antoine Bollet worked on a kind of similar idea where they tried to build EDF models inspired by the unitary gas and the just mentioned works from them. So now come to introducing our strategy. We took this inspiration by what is called in condensed matter DFT the Jacob's ladder approach by Perdue and collaborators, and which is quite well established actually in electronic system. Here we are not trying to reproduce step by step all the details of the condensed matter strategy, but we want to stick to two principles which inspire that approach. That is, we want to build the EDF step by step. That is, we want to start with a simple approximation and then try to introduce complexity progressively, which is a kind of in contrast with empirical EDFs that typically choose a fixed form, say once for all, and then fit it. And second element is that we want to try to exploit ab initio simulations of model systems to put constraints to the DF. That is, in our view, we would like to use experimental data just at the end, but put as tighter constraints using ab initio instead. So just to make things concrete, the first step is what is called local density approximation. You probably heard about that in some talks, which basically is a way to convert the equation state of infinite nuclear matter into an EDF model. And then I will describe what we are working on now, which we call generically gradient approximation, where instead we use perturbed nuclear matter calculations to fix the gradient part of the EDF. Just a warning, because it must be remembered that the nuclear interaction is not unique and it's very complicated. So there are many more difficulties than in the Coulomb interaction case, where this strategy was the general approach was thoroughly discussed. So I will describe a bit better the local density approximation, first of all. Here, the idea is that the potential energy density in a generic system, so nucleus or a generic finite or an infinite system, has the same expression as in infinite matter. That is the assumption of all kinds of local density approximations in different flavors. That implies that the equation state, which is a function of rho is the total density and beta is the isospin asymmetry parameter, which basically quantifies the difference between the neutron and proton densities, because you remember that we have two isospin flavors in two isospin species in nuclear system. And so here there's an example of the equation of states of in the two limiting cases, which are typically studied, this is pure neutron matter and symmetric nuclear matter. And symmetric nuclear matter basically means that the isospin asymmetry is zero, so there's an equal number of protons and neutrons. It is also useful, actually, just for notation, to split the equation of state into a kinetic free Fermi gas, say, and a potential energy per nucleon contributions. Then this simple formula gives the idea of the local density approximation, because this is basically the energy density where we have exploited the expression of the potential energy in neutron matter. And this model can now be applied everywhere, not just to infinite matter, but in any system. So we are computed the equation state using two different ab initio techniques and actually two different nuclear interactions. Here I will show mostly the results which come from using self-consistent Green's function with the N2LO SAT interaction. But actually we've also discussed auxiliary field diffusion Monte Carlo calculations with the argon for interaction plus a free body contribution. So I just remember for the cold atom people that the important thing to know about symmetric matter is that it saturates, that is, it admits a minimum in the equation of state, basically, while pure neutron matter is strictly increasing. And it's important to remember that symmetric matter is an essential element for nuclei, okay, because nuclei are for the most part close to they are quite symmetric in the number of protons and neutrons. So neutron matter, which is the most studied, I think, from ab initio, is important, but it's not enough in our view. So also it would be interesting to push also the studies of symmetric matter. So I just give you a few technical details on how we find the parameterization for the equation of state. So the point is that in practice we have no analytical expressions and few analytical constraints on the nuclear matter equation of state. So we decided to go this way. Okay, we split the kinetic and potential terms, and that's fine. Then we assume that V is quadratic in the isospin asymmetry beta, and that is quite commonly assumed. It should be work well. And then we make the following ansatz. That is, we try to express the potential as a polynomial of the Fermi momentum, or which is actually proportional to rho to the 1/3. So our potential term looks like this. And now the point is that In many studies, the potentials, which we call generically gamma, are just fixed from scratch. While we try to do something more, in a sense rigorous, that is, we explore the set of different combinations of gamma. So we change both the number of terms in the parameterization and the powers included in this scheme. And with a actually quite simple but quite effective model selection procedure, we evaluated the best set of exponents. So for example, I can just show you here that for the curves which I showed before, we can find a quite good 5-parameter interpolation. So there's basically a really small difference between the interpolation, this 5-parameter model, and the ab initio data. So once we are satisfied with the parameterization, we can make calculations with the local density approximation scheme. So I will show you here some results. We studied actually ground state energies and radii of a set of closed shell nuclei, and these results are based on the end-loss-up interaction. Here I show the discrepancy with respect to experiment. So experiment is the flat line at 0, and here you can see that ab initio gets very close to experiment, but it's actually limited to medium mass systems. So for example, here we get to a mass of 50 nucleons, but no more than that, basically. DFT, as I was saying, instead can be applied everywhere. And you can see that local density approximation is the basic scheme in a sense. And so we cannot expect a close agreement with experiment, but what is interesting is that is the trend, because basically as we go to high mass nuclei, to heavy nuclei, the discrepancy shrinks and shrinks, which is what you expect, because basically local density approximation neglects surface effects, which are much more important in light nuclei than in heavy nuclei. As we get to larger systems, the surface plays a somewhat less important role. So as I was saying, that's fine. We get sensible results, but still our local density approximation is not highly accurate. So as I was anticipated, what is missing? Basically, nuclei are finite systems. And so this translates into the fact that, which is well known in DFT, that a dependence on the gradients of the density, nabla rho, must be introduced in the energy function. And while LDA is more or less established, here is not that clear how to fix the gradient terms. Also, you can guess that in uniform matter, the gradients of the density is 0. Also, the spin orbit density is 0. So if we want to get information on this contribution, we must study non-uniform systems. And so in empirical EDFs, this information in non-uniform system basically comes from using nuclear observables. As I was saying, if you fit on finite nuclei data, you basically get information on these non-uniform effects. In our approach, instead, we want to study inhomogeneous systems ab initio. And in particular, I will now describe that we're going to study nuclear matter perturbed by periodic potential. I just mentioned in passing from discussions this week that in some works, other systems were considered to give information on the EDF description, like, for example, neutron-proton drops, which is basically matter confined in a harmonic potential, in particular neutron drops, actually. And also semi-high infinite matter was suggested at some point. And in many-body theory, this is called the static response problem. And one of the organizers, Alex Getzelis, has worked a lot on that, and I'll talk about that in a few slides. So the idea is now that if we can get the static response, we can get also information on an ADF description, which includes these terms, these very important terms. So a brief description of perturbed nuclear matter, first of all. Basically, the idea is that we add a small external sinusoidal potential to the nuclear matter Hamiltonian. And I mean, it's enough to consider a monochromatic potential, basically, because any potential could be written as a Fourier series, but just one is the basic model we can study, and also it's quite physically motivated. And so the idea is that here we have unperturbed matter at which means that the density is flat as a function of the position. But if we introduce an external potential, the red one, also the density of the system gets modulated. So it's no more uniform, but it's kind of sinusoidal. In particular, if the perturbation is small enough and we can trust the linear response, we expect the amplitude of the fluctuation of the density to be proportional to the external strength, while the energy of the perturbed system varies quadratically. So, for example, these results were obtained with slide for interaction with slide for EDF, which is commonly used in nuclear physics. And so here you can see uniform matter and that the energy gets decreasing while the perturbation strength is turned on. And this quantity chi of Q is called the static response function, basically governs the behavior of both the density and the energy, at least when when a linear response is valid, so in the small perturbation regime. So just a few more words on the static responses. Was saying Gezelis has studied extensively, for example, in these two papers and some others, the static response of neutron matter. And I want just to give you an idea, of a very brief idea on about how this calculation go. So in practice, auxiliary field diffusion Monte Carlo was used, and calculations were performed with 66 neutrons. That is commonly done in nuclear matter, and neutrons were put in a box under periodic boundary conditions. The point is that, okay, due to periodic boundary conditions, also the momentum is quantized, so you can see only discrete points and not a continuous curve, basically. And also, it's important to know that much care must be taken if one wants to extrapolate from the finite number of particles to the thermodynamic limit. And I just show you here why. This is just an example of DFT response. So you can see that 66 particles have a very different behavior than the thermodynamic limit, for example. And this justifies many efforts which were done to go from the bare results to the raw results to these points, which instead were extrapolated to the thermodynamic limit with some recipes by Gezelis and collaborators. So just so now, what I'm working on right now is to adapt basically the techniques of Gezelis and others that I presented earlier to perform nuclear matter calculation, and it's important in both neutron matter and symmetric matter. We are now working a bit mostly on auxiliary field, but we plan to also study Green's function, the study response in the Green's function formalism. And our goal is that the LDA is fixed, basically, what I show here. And then we can add the extra contribution, which include the gradient, actually Laplacian, but basically the gradient terms, the gradients of the densities, and the spin orbit contributions. And the idea is that we want to have an ab initio data set made of the energies at different strengths and momenta of the external perturbation. Just like here, you can see that here, the energy is a function of V, was shown for two different cubes, for example. And these were our preliminary calculations. And then the idea is that we want to match the energy. We obtain a finite number of particles with DFT calculation with the same number of nucleons. And from that, we hope to get information about the unknown coefficients. I just add that neutron matter and symmetric matter, I didn't describe that, are basically decoupled, so we can fit separately one or the other system. So I just come to a conclusion and just summarize what my talk. So we are developing a ladder, this is called Jacob's ladder, of ab initio constrained models of nuclear energy functionals. We have implemented and discussed the local density approximation, which is the first rank. And now we are studying the response of nuclear matter per weak static perturbation to get information on the gradient terms. And as our near-term goals are completing the gradient approximation and then trying to apply it not only to the ground state, but also to collective states, for example, in an RPA scheme. So I just now to a conclusion, and thank you for your attention. Just this is the paper we published and our collaborators. Thank you.
Well, thank you much. questions or suggestions from the audience? Yes.
So I have a question. May I ask?
We do have one here. 1 second.
Of course.
Yeah, hello, Michael Orbach from Marseille. I had a question about, you had in the beginning, when you showed the more general things of density functional theory, you had the usual thing where appeared also the kinetic energy density. Now it looks to me, if I understood correctly, that in your theory or in the functional that you are developing, you do not plan to put an effective mass, right?
You're right.
You have no such term which you have written here with effective mass.
Okay. Actually, the effective mass is a bit tricky because it enters both the equational state and finite system. So while, for example, nabla rho enters only non-uniform systems, tau is kind of mixing both uniform and non-uniform systems. So yeah, we're thinking about that, but we have not come to a solution yet. So we're focusing more on the other terms. Also, it's true, I think there is not an evidence that the effective mass is very far from one, so maybe it can mimic by other terms. So we're thinking about that, but that's not the first step we are planning to do for now.
Alex, you want to ask a question?
Excellent, thank you. First of all, thank you for a very interesting talk. I have a question that's conceptual, and I want to preface it by saying it's fine if you don't know how to answer it, it's just food for thought, right? At the very big picture level, so you started by saying you want to do step-by-step approximations and so on. Is there a fear that the local density approximation and the gradient approximation do not commute? Like if you take the gradient approximation, if you start with a finite system, and go the other way, you won't get the same answer.
Yes. Okay, I get the point. Okay. So there's a lot. Let's say this way. Let's put it this way. There's a lot of experience in nuclear DFT of empirical models. So we know that basically they in several respects they have limitations. I mean, but in several respects they work well and they're fit on nuclei. But I think that our perspective is that there were many studies that tried to improve empirical EDFs with using larger data sets, more advanced statistical tools, and things like that. And you get some improvements, but not really great improvements. So we are trying to push this other strategy to see if instead taking a different perspective, maybe we can find some new way to get better models. So it's a complementary strategies would be to do machine learning, push on statistics, but some studies show that, okay, that's an interesting way, but it's somewhat blocked. I mean, there hasn't been so much clear progress in the last few years. So maybe, yeah, I mean, it could not work that well in the end. We don't know yet, but we are interested in doing this. And actually, there are many differences, I know, but for example, in condensed matter, they push this Jacob's ladder strategy quite far. So starting from the homogeneous gas, then trying to put constraints on the gradients. So we're not mimicking the details, obviously, but a bit of the philosophy could be interesting to push a bit forward.
Okay, I think I'm satisfied. So basically what you're saying is that, you know, this has been a successful strategy in another field. So it's worth seeing if it works for nuclear, right?
Exactly.
Excellent. Thank you.
Thank you for your question.
If you further your opinion for neutron matter, then as you showed, there are two terms in functional that will contribute this surface term and spin orbit.
Yes.
How can you disentangle between the contribution to these two?
That's a good question. I think so far it's difficult to disentangle between them, and because I think that in more empirical approaches you have to look at, for example, single particle properties, something like that, to really disentangle those. So I'm not sure how much we can do about that in infinite using a perturbed nuclear matter. What I can tell is that the spin orbit is quite important because unfortunately I don't have the plot, but this thermodynamic limit result is analytical by Alessandro Pastore and others. So that's basically a very complicated formula, but you get the exact answer. And you can see that if you turn off a spin orbit, this includes spin orbit, but if you turn it off, you get quite a sensible difference. So we think that we are somehow sensible to spin orbit. It's not really small. It can have some effect on neutron matter, on perturbed matter calculations. But yeah, you're true. I mean, you got a good point because you're not. I'm not sure how to disentangle those effects.
Wonderful. Thank you, Francesco.